Hello and welcome to this lecture on Kubernetes pods. Before we head into understanding pods, we would like to assume that the following have been set up already. At this point, we assume that the application is already developed and built into Docker images, and it is available on a Docker repository like Docker Hub, so Kubernetes can pull it down. We also assume that the Kubernetes cluster has already been set up and is working. This could be a single node setup or a multi-node setup, doesn't matter. All the services need to be in a running state. As we discussed before, with Kubernetes, our ultimate aim is to deploy our application in the form of containers on a set of machines that are configured as worker nodes in a cluster. However, Kubernetes does not deploy containers directly on the worker nodes. The containers are encapsulated into a Kubernetes object known as pods. A pod is a single instance of an application. A pod is the smallest object that you can create in Kubernetes. Here we see the simplest of simplest cases where you have a single node Kubernetes cluster with a single instance of your application running in a single Docker container encapsulated in a pod. What if the number of users accessing your application increase and you need to scale your application? You need to add additional instances of your web application to share the load. Now, where would you spin up additional instances? Do we bring up a new container instance within the same pod? No. We create new pod altogether with a new instance of the same application. As you can see, we now have two instances of our web application running on two separate pods on the same Kubernetes system or node. What if the user base further increases and your current node has no sufficient capacity? Well, then you can always deploy additional pods on a new node in the cluster. You will have a new node added to the cluster to expand the cluster's physical capacity. So what I'm trying to illustrate in this slide is that pods usually have a one-to-one relationship with containers running your application. To scale up, you create new pods, and to scale down, you delete existing pods. You do not add additional containers to an existing pod to scale your application. Also, if you're wondering how we implement all of this and how we achieve load balancing between the containers, etc., we will get into all of that in a later lecture. For now, we are only trying to understand the basic concepts. We just said that pods usually have a one-to-one relationship with the containers. But are we restricted to having a single container in a single pod? No. A single pod can have multiple containers except for the fact that they're usually not multiple containers of the same kind. As we discussed in the previous slide, if our intention was to scale our application, then we would need to create additional pods. But sometimes you might have a scenario where you have a helper container that might be doing some kind of supporting task for our web application, such as processing a user-entered data, processing a file uploaded by the user, etc. And you want these helper containers to live alongside your application container. In that case, you can have both of these containers part of the same pod, so that when a new application container is created, the helper is also created, and when it dies, the helper also dies since they are part of the same pod. The two containers can also communicate with each other directly by referring to each other as localhost, since they share the same network space. Plus, they can easily share the same storage space as well. If you still have doubts in this topic, I would understand if you did, because I did the first time I learned these concepts. We could take another shot at understanding pods from a different angle. Let's, for a moment, keep Kubernetes out of our discussion and talk about simple Docker containers. Let's assume we were developing a process or a script to deploy our application on a Docker host. Then we would first simply deploy our application using a simple docker run python app command, and the application runs fine and our users are able to access it. When the load increases, we deploy more instances of our application by running the docker run commands many more times. This works fine and we're all happy. Now, sometime in the future, our application is further developed, undergoes architectural changes, and grows and gets complex. We now have a new helper container that helps our web application by processing or fetching data from elsewhere. These helper containers maintain a one-to-one relationship with our application container and thus needs to communicate with the application containers directly and access data from those containers. For this, we need to maintain a map of what app and helper containers are connected to each other. We would need to establish network connectivity between these containers ourselves using links and custom networks. We would need to create shareable volumes and share it among the containers. We would need to maintain a map of that as well. And most importantly, we would need to monitor the state of the application container, and when it dies, manually kill the helper container as well, as it's no longer required. When a new container is deployed, we would need to deploy the new helper container as well. With pods, Kubernetes does all of this for us automatically. We just need to define what containers a pod consists of, and the containers in a pod by default will have access to the same storage, the same network namespace, and same fate, as in they will be created together and destroyed together. Even if our application didn't happen to be so complex and we could live with a single container, Kubernetes still requires you to create pods. But this is good in the long run, as your application is now equipped for architectural changes and scale in the future. However, also note that multi-pod containers are a rare use case, and we're going to stick to single containers per pod in this course. Let us now look at how to deploy pods. Earlier, we learned about the kubectl run command. What this command really does is, it deploys a Docker container by creating a pod. So it first creates a pod automatically and deploys an instance of the nginx Docker image. But where does it get the application image from? For that, you need to specify the image name using the -- image parameter. The application image, in this case the nginx image, is downloaded from the Docker Hub repository. Docker Hub, as we discussed, is a public repository where latest Docker images of various applications are stored. You could configure Kubernetes to pull the image from the public Docker Hub or a private repository within the organization. Now that we have a pod created, how do we see the list of pods available? The kubectl getPods command helps us see the list of pods in our cluster. In this case, we see the pod is in a container creating state and soon changes to a running state when it is actually running. Also remember that we haven't really talked about the concepts on how a user can access the nginx web server. And so in the current state, we haven't made the web server accessible to external users. You can, however, access it internally from the node. For now, we will just see how to deploy a pod, and in a later lecture, once we learn about networking and services, we will get to know how to make this service accessible to end users. That's it for this lecture. We will now head over to a demo, and I will see you in the next lecture. In this demo, we're going to deploy a pod in our Minikube cluster. Now, as we discussed, a pod is the most basic and the smallest unit in Kubernetes. So we will use the kubectl command line utility to interact with the Kubernetes cluster. Now, if you followed our demo earlier of deploying a cluster using Minikube, then you already have the kubectl command line utility configured to work with the cluster. We will run the command kubectl run nginx, which is the name of the pod, -- image equals to nginx. Now here is where we specify the Docker image to be used. While the pod name could be anything, the image name has to be the name of an image available at Docker Hub or any other container registry. You can additionally specify a tag for the image name or a different address to an image hosted on another registry if the image is hosted in a place that's other than Docker Hub. Okay, so once we run this command, we see a pod by the name nginx has been created, and you can check the status using the kubectl get pods command. Now here you can see the column name, which is nginx, the status is running, and we see that there is a ready column which shows the number of containers in a ready state. We also see if the container has restarted since it was created and how long has the pod been running. We can get more information related to the pod by running the kubectl describe pod nginx command. And you'll notice that this provides a lot more information as compared to the get command. So for example, the name of the pod is nginx. It shows any labels that has been assigned to this pod. So this was created by default when we ran the run command. It shows when it was started. It shows the node that it is assigned to, along with the IP address of the node. So in this case, we just have a single node cluster set up using Minikube, and the node name is Minikube, and that is the IP address of this worker node. Secondly, it also shows the IP address of the pod itself. So in this case, the pod is assigned an IP of 172.16.0.3. We'll cover more about the IP addresses of the pod later in the networking section. Now moving on, we can see that it displays information related to the container. So we know that there is a single container which uses the image nginx. If there were multiple containers, we would list them here. I'll explain about creating a pod with multiple containers in the upcoming lectures. But here we can also see that the nginx image was pulled from Docker Hub. And if you scroll all the way to the bottom, you'll see additional information called events. And here you see the list of events that occurred since the pod was created. It went through multiple stages before it started. We can see that the pod was assigned to the Minikube node. If there were multiple nodes, you would see which node the pod was assigned to here. And then it entered the pulling phase where the nginx image was pulled down from Docker Hub successfully. And then the container called nginx was created and started. Now there is one other command that we can use to check the status of the pod, and that is the same command as before, the kubectl get pods command, but with the -wide option. And this provides additional information such as the node where the pod is running and the IP address of the pod as well. So this is the internal IP address of the pod itself. So each pod gets an internal IP of its own within the Kubernetes cluster, but more on that later. That was a quick demonstration on how to run a pod in Minikube environment. In the upcoming videos, we will see how to create a pod using a YAML definition file. Hello and welcome to this lecture. In this lecture, we take a look at what YAML files are. If you are familiar with YAML already, feel free to skip this section and head over to the next section. If you have not worked with YAML in the past, I would highly recommend going through this because the rest of the course depends entirely on YAML. If you have worked with other data structure formats like XML or JSON, you should be able to easily pick it up. Don't worry if you haven't worked on any of these, you should still be able to easily pick it up going through the coding exercises that accompany this course. A YAML file is used to represent data, in this case configuration data. Here is a quick comparison of a sample data in 3 different formats. The one on the left is XML, where we display a list of servers and their information. The same data is represented in JSON format in the middle, and finally in YAML format to the right. Take a minute to compare the 3 formats. Let's take a close look at YAML. If you take the data in its simplest form, such as key-value pair, this is how you would define it in YAML. key and value separated by a colon. The keys are fruit, vegetable, liquid, and meat, and the values are apple, carrot, water, and chicken. Remember, you must have a space followed by a colon differentiating the key and the value. Let's take a look at how an array is represented. We would like to list some fruits and vegetables. We would say fruits followed by a colon. On the next line, enter each item with a dash in the front. The dash indicates that it's an element of an array. How about a dictionary? A dictionary is a set of properties grouped together under an item. Here we try to represent nutrition information of two fruits. The calories, fat, and carbs are different for each fruit. Notice the blank space before each item. You must have equal number of blank spaces before the properties of a single item, so they are all aligned together. Let's take a closer look at spaces in YAML. Here we have a dictionary representing the nutrition information of banana. The total amount of calories, fat, and carbs are shown. Notice the number of spaces before each property that indicates these key value pairs fall within banana. But what if we had extra spaces for fat and carbs? Then they will fall under calories and thus become properties of calories, which doesn't make any sense. This will result in a syntax error which will tell you that mapping values are not allowed here because calories already have a value set which is 105. You can either set a direct value or a hash map. You cannot have both. So the number of spaces before each property is key in YAML. You must ensure they're in the right form to represent your data correctly. Let's take it to another level. You can have lists containing dictionaries containing lists. In this case, I have a list of fruits and the elements of the list are banana and grape. But each of these elements are further dictionaries containing nutrition information. A lot of students new to YAML have reached out to me asking when to use a dictionary or a list. So let me explain this a little bit better. First of all, it is important to understand that all of what we discussed so far, such as XML, JSON, or YAML, are used to represent data. It could be data about an organization and all of its employees and their personal details, or it could be data about a school and all of its students and their grades, or it could be data about an automobile manufacturing company and all of its cars and its details. It could be anything. Let's take an example of a car. A car is a single object, and it has properties such as color, model, transition, and price. To store different information or properties of a single object, we use a dictionary. In this simple dictionary, I have properties of the car defined in a key value format. This need not be as simple as this. For example, in case we need to split the model further into model name and make year, you could then represent this as a dictionary within another dictionary. In this case, the single value of model is now replaced by a small dictionary with two properties, name and year. So this is a dictionary within another dictionary. Let's say we would like to store the name of 6 cars. The names are formed by the color and the model of the car. To store this, we would use a list or an array as it is multiple items of the same type of object. Since we are only storing the names, we have a simple list of strings. What if we would like to store all information about each car? Everything that we listed before, such as the color, model, transition, and price. We will then modify the array from a list of strings to a list of dictionaries. So we expand each item in the array and replace the name with the dictionary we built earlier. This way, we are able to represent all information about multiple cars in a single YAML file using a list of dictionaries. So that's the difference between dictionary, list, and list of dictionaries. I hope you understood the difference between the three and when to use each of these. Before we head over to exercises, let's take a look at some key notes. Dictionary is an unordered collection, whereas lists are ordered collection. So what does that mean? The two dictionaries that you see here have the same properties for banana. However, you can see that the order of properties, fat and carbs, do not match. In the first dictionary, fat is defined before carbs, and in the second dictionary, carbs comes first, followed by fat. But that doesn't really matter. The properties can be defined in any order, but the two dictionaries will still be the same as long as the values of each property match. This is not the same for lists or arrays. Arrays are ordered collection, so the order of items matter. The two lists shown are not the same because apple and banana are at different positions. This is something to keep in mind while working with data structures. Also remember, any line beginning with a hash is automatically ignored and considered as a comment. We are now ready to head over to the coding exercises and have fun playing with YAML files. Hello and welcome to this lecture. In this lecture, we will talk about creating a pod using a YAML-based configuration file. In the previous lecture, we learned about YAML files in general. Now we will learn how to develop YAML files specifically for Kubernetes. Kubernetes uses YAML files as inputs for the creation of objects such as pods, replicas, deployments, services, etc. All of these follow a similar structure. A Kubernetes definition file always contains 4 top-level fields: the API version, kind, metadata, and spec. These are the top-level or root-level properties. These are also required fields, so you must have them in your configuration file. Let us look at each one of them. The first one is the API version. This is the version of the Kubernetes API we are using to create the object. Depending on what we are trying to create, we must use the right API version. For now, since we are working on pods, we will set the API version as v1. Few other possible values for this field are apps/v1 beta, extensions/v1 beta, etc. We will see what these are for later in this course. Next is the kind. The kind refers to the type of object we are trying to create, which in this case happens to be a pod. So we will set it as pod. Some other possible values here could be replica set or deployment or service, which is what you see in the kind field in the table on the right. The next is metadata. The metadata is data about the object, like its name, labels, etc. As you can see, unlike the first two where you have specified a string value, this is in the form of a dictionary. So everything under metadata is intended to the right a little bit, and so names and labels are children of metadata. The number of spaces before the two properties, name and labels, doesn't matter, but they should be the same as they are siblings. In this case, labels has more spaces on the left than name, and so it is now a child of the name property instead of a sibling, which is incorrect. Also, the two properties must have more spaces than its parent, which is metadata, so that it's intended to the right a little bit. In this case, all three of them have the same number of spaces before them, and so they are all siblings, which is not correct. Under metadata, the name is a string value, so you can name your pod my app pod. And the labels is a dictionary, so labels is a dictionary within the metadata dictionary. And it can have any key and value pairs as you wish. For now, I have added a label app with the value my app. Similarly, you could add other labels as you see fit, which will help you identify these objects at a later point in time. Say, for example, there are hundreds of pods running a front-end application and hundreds of pods running a back-end application or a database. It will be difficult for you to group these pods once they are deployed. If you label them now as front-end, back-end, or database, you will be able to filter the pods based on this label at a later point in time. It's important to note that under metadata, you can only specify name or labels or anything else that Kubernetes expects to be under metadata. You cannot add any other property as you wish under this. However, under labels, you can have any kind of key or value pairs as you see fit. So it's important to understand what each of these parameters expect. So far, we have only mentioned the type and name of the object we need to create, which happens to be a pod with the name myAppPod. But we haven't really specified the container or image we need in the pod. The last section in the configuration file is the specification section, which is written as spec. Depending on the object we are going to create, this is where we would provide additional information to Kubernetes pertaining to that object. This is going to be different for different objects, so it's important to understand or refer to the documentation section to get the right format for each. Since we are only creating a pod with a single container in it, it is easy. Spec is a dictionary, so add a property under it called containers. Containers is a list or an array. The reason this property is a list is because the pods can have multiple containers within them, as we learned in the lecture earlier. In this case though, we will only add a single item in the list, since we plan to have only a single container in the pod. The dash right before the name indicates that this is the first item in the list. The item in the list is a dictionary, so add a name and image property. The value for image is nginx, which is the name of the Docker image in the Docker repository. Once the file is created, run the command kubectl create -f followed by the file name, which is poddefinition.yaml, and Kubernetes creates the pod. So to summarize, remember the 4 top-level properties: API version, kind, metadata, and spec. Then start by adding values to those depending on the object you are going to create. Once we create the pod, how do you see it? Use the kubectl getPods command to see a list of pods available. In this case, it's just one. To see detailed information about the pod, run the kubectl describe pod command. This will tell you information about the pod, when it was created, what labels are assigned to it, what Docker containers are part of it, and the events associated with that pod. That's it for this lecture. We will now head over to a demo, and I will see you in the next lecture. In this demo, we're going to create a pod again, but this time, instead of making use of the kubectl run command, we are going to create it using a YAML definition file. So our goal is to create a YAML file with the pod specifications in it. Now, there are many ways to do it. You could just create one in any text editor. So if you're on Windows, you could just use Notepad, or if you're on Linux, as I am, just use a native editor like VI or Vim. An editor with support for YAML language would be very helpful in getting the syntax right. So instead of Notepad, a tool like Notepad++ in Windows or Vim in Linux would be better. Now I'll talk more about tips and tricks and other tools and IDEs that can help with this more in the upcoming lectures. For now, let's take with the very basic form of creating a YAML file using a VI editor on my Linux system. So here I am on my Linux terminal, and I'm going to make use of Vim text-based editor to create this pod definition file. So the name of the file I'm going to call as pod.yaml, and as seen in the lecture, we will start off with the 4 root level elements, or the root level properties that we saw, which are API version, kind, metadata, and spec. So we know that the value for API version for a pod is v1. The kind is pod with a capital P, so it is case sensitive, so that's important. And metadata is a dictionary, and it can have values where we define the name of the pod. So I'm going to use name as nginx, and we can have additional labels that we can specify under it. So labels again is also a dictionary, and it can have as many labels as you want under it. So we can specify a label which is a key value pair, such as app and nginx. And we can also add more labels like tier and set it to front end, anything that can help us group this particular pod. Next, we have to define the spec. So spec is also a dictionary. It has an object called containers. So before we move on to that, we have to make sure that we get the indentation right. For example, the app and tier are children of the labels property. So it has to be in the same kind of vertical line here. And similarly, under metadata, you have name and labels, which are the children of metadata. So they both have to be within the same vertical line. So you have to make sure that the spacing is correct. Typically, it would be 2 spaces or a tab, but it is recommended not to use tabs. So always stick to 2 spaces and stick to that throughout. So the next thing that we're going to configure is the container. So a container is a list of objects. Now we first give it a name. Note that this is the name of the container within the pod, and there could be multiple containers, and each can have a different name. So one container could be named app, and another container could be named helper. Any name that makes sense to you. We're going to use the same name as that of the container image, so we will just name it nginx. And the second object that we're going to add here is the image name, which is the Docker Hub image name of the container that we're going to create. So the image name is again nginx. If you're using other registries than Docker Hub, then make sure to specify the full path to that image repository here. Now remember that we can add additional containers to the pod as well. So if you have to do that, we have to declare the secondary element to the list, which would be the second object in the list. So here I can, for example, add a busybox container using the busybox image, and that would be the second element of the array. So in this case, we're going to stick to one single container. So I'm going to just delete that. And I'm now going to hit escape :WQ to save this file, and we will just use the cat command to make sure that the file was created with the expected contents. So make sure the format is correct. So the name and labels are children of metadata, and you can see that they are on the same kind of vertical line. And similarly, labels have 2 children, which are the 2 labels, app and tier. And spec has a list, and we are defining it as a list with a hyphen followed by the objects. So we can make use of the kubectl create command or the kubectl apply command. So the create and apply command kind of works the same if you're creating a new object, right? You can either use create or you can use apply. It doesn't matter. And we pass in the file name using the -f option. And here we can see that the pod has been created. So let's check the status real quick. And you can see that it's in container creating state. And then when we check again, we see that it's in a running state. And as before, if you want to get more details about the pod, you can always run the kubectl describe command and specify the name of the pod, and you should get a much more in-depth information about the pod. Okay, so that's it for this demo. In the next section, we will learn some tips and tricks of developing YAML files easily using IDEs. In the previous demo, we used the Vim command line editor to create our pod definition file. We created a pod called Nginx with a couple of labels, and we used the Nginx image. Now, while this works well, the Vim editor is quite basic, and it can be quite difficult to make use of them if you want to create and edit long or even large number of YAML files. The same goes with Notepad or other tools in Windows. They are very basic and prone to errors. They don't really tell you if you made a mistake. The Kubernetes object definition files using YAMLs can be developed much easier using IDE tools. Now, there are many IDEs out there that are free to use, such as those from JetBrains, IntelliJ IDEA, and PyCharm. Atom is another free tool. Eclipse or NetBeans that a lot of Java developers use. And all of these come with support for YAML files, and they will help in highlighting errors in a YAML file and making sure that you develop them right. But they won't natively tell you if there are errors within the Kubernetes manifest files that you're developing. For example, if you typed in a wrong property name, or if you're using a dictionary instead of a list. And that's where you need some kind of an extension or a plugin that could help point those out for you. So those tools that can first verify structure of your YAML file, the syntax, making sure that works fine, and also point out errors related to Kubernetes, right? Support for Kubernetes. And so these IDEs come with support for extensions and plugins that can help with that. And those plugins could either be free or paid. Now, one IDE that we found that is freely available and works on all different operating systems and also has a free extension for YAML validation for Kubernetes is the Microsoft Visual Studio Code IDE. It's easy to set up and get started, and so we will use that as our IDE for the rest of the demos in this course. Now, you don't necessarily have to use the same tool. Feel free to use any IDE of your choice and try to find a plugin or extension that can help with developing Kubernetes YAML files for the IDE of your choice. Okay, so in this demo, we're going to first install VS Code. So here I'm at the code.visualstudio.com website, and since I'm running on an Ubuntu-based distribution, I'm going to download the Debian package. It should automatically list the right version to download for you depending on your operating system. As it says here, Visual Studio Code is free and open source software. We will wait for the download to complete. The download has been completed, and since it's a Debian package, I'm just going to install it directly on my system. So let's wait for the installation to complete. The installation has been completed now, and I'm going to launch VS Code. Once open, this is what it would look like after a fresh install. So we will go to the extensions section first and search for YAML and look for the extension which is published by Red Hat. This is the extension that has support for Kubernetes YAML files. Now, in most cases, this particular YAML extension is installed by default, but if it's not in your case, then you'll see that here, and you can go ahead and click on the install button to install and enable it. Now, before we get started with developing Kubernetes definition files,
using this extension, we have to make a small change in our settings to configure VS Code to use the YAML extension for Kubernetes files, right? So by default, this YAML extension provides basic YAML validation functionality. To enable Kubernetes support, we must configure it to work with YAML files that we plan to develop. So there are two ways to do it. One way is to click on this gear icon on the YAML file, YAML extension, and go to extension settings and scroll all the way to the bottom where there is a YAML schemas option, and click on the edit in settings.json file option. Now this will take you to the settings.json file. This file may or may not have some contents already based on other extensions or configurations that you might have already done. So if it's a new installation, it might look empty like this. So whatever it may be, our goal is to simply add a small section of code into this file. It should have the YAML schema section if you came here following the path that I showed. We're going to add an entry for Kubernetes schema support. We add a schema for Kubernetes for all YAML files using the star.yaml pattern. Okay, so we're basically saying that we want to use Kubernetes schema for all YAML files that we develop using VS Code. Now, if you don't really want to do that, if you don't want to use the Kubernetes schema for all the YAML files, instead, if you plan to create Kubernetes files using a particular pattern, then you can specify that pattern or extension here. Okay, so we will just leave it as it is. Now this is case sensitive as well, so make sure that you use all small case for the word Kubernetes in this file. So one thing that you'll have to do is to reload the Visual Studio Code after making this change so it takes effect. So just exit and restart VS Code at this point. Another way to get to the settings .json file is to use the Control+P shortcut key, where a search bar would open at the top, and then there you type in settings.json and then go to the settings.json file from there. But if this doesn't work, use the gear icon approach that I just showed. Okay, so here again, as you can see that this file has already been saved, so we don't have to do anything else. So what I'm going to do is I'm going to close this Visual Studio Code editor, and I'm going to open it up again. Once it is up, I'm just going to make sure that the YAML extension is enabled. So we don't have an option to enable or install here, which means that it is already enabled. Okay, so let's now open a folder on our system. So in this case, I'm going to open the directory called Kubernetes for Beginners, which is where our pod definition file resides, the one that we created earlier with the Vim editor in the previous demo. For the purpose of this demonstration, let's create another file. So click on a new file and let's call it nginx.yaml. So now we're going to create a new YAML file using the Visual Studio Code editor, and we'll make use of the YAML extension that we just installed. So we'll see how that works. But to make this work, first we have to create the first root level property, or the element called API version, and which for pod will be v1. Now once you put that in, the Kubernetes support part of the YAML extension we installed kicks in. And then it'll start suggesting additional properties and performing validations. So note that you must have that one line in, the first line in, for the rest of the suggestions to work. Okay. Now if I type in K for kind, it will suggest the available root level properties starting with K, and it suggests kind. So if I just press tab, it will auto finish it, auto complete it for me. And then press Control spacebar and type P, and it will show you the list of all different objects that are available starting with P. So in this case, we're interested in pods. So I'm going to select pod. And if I hit enter, and press M, then metadata is suggested, and again hit control space and it will suggest supported options. The YAML extension knows that this metadata is a dictionary, so it has already kind of intended the lines to the right for me. So I'm going to add a name field here, and again we use the control space to complete, and you will notice that there is this error indicated here below the name, and it is expecting a string type field here. So as long as this is empty, it will continue to show that error. So let me add a name of the pod, which could be nginx-2, and as soon as I complete that, you'll see that the error indicator is gone. So now again, if I hit enter, you'll see that it maintains the right indentation, and it keeps it at the same vertical line as the child of metadata, which is name. So now the next one that I'm going to add is label. Again, press control space and it will autocomplete the label for me. And now if I press tab, it knows that labels is also a dictionary, so it has maintained that additional formatting. Now here it won't suggest any properties or labels because labels could really be anything. So it's up to you to decide what labels to add or for that pod. And that's why there's no suggestions here. Now I will add a label such as environment and set it to production, so that that would be the only label that I want to add right now. So now to go back to the root level, again I'm just going to press backspace twice, and it takes me to the level of metadata and in the same vertical line. So now the next thing that we want to add is a spec section. Again, we make use of the control space shortcut, and it will suggest options. Note that if the suggestion does not include what you're expecting, then there is probably something wrong with the format of your file. So you're probably not in the right place to add that file. So that's an additional support the extension provides to prevent you from creating a file with an incorrect structure. So I hit tab to choose that suggestion, and the extension knows that for pod, what comes directly underneath the spec section is the containers section, and that containers is a list, so it has created a list here with the first element already populated and waiting on you for the name. So let us set a value for the name of the container. Here we can use nginx, and if I hit enter, it maintains the right indentation for me to add another container, and say we would like to specify an image for the first container. So if I make a mistake here, for example, if I add an image property and set it to say nginx, again it knows that there is an error, because, and if I just highlight on top of that, it says bad indentation for a mapping entry. So we have to make sure that all properties of a single container are correctly aligned under it. One thing to remember here is that it doesn't really validate if the image name that you're using are valid image names. So the names of images you specify, or the names that you use for your pods or containers, or the labels that you assign to objects could really be anything. So those are not validated, and it won't give you an error if you used an image that's not available on Docker registry. So that's up to you to make sure that you get those right. However, it does validate certain fields that has to have values supported by Kubernetes, such as the kind field at the top being set to pod or a deployment. So if you used a value other than a kind that is supported by Kubernetes, then it will throw an error. Okay, so now if you want to add another element to this array, we can do that by hitting enter and using backspace to go back to the same level as the previous element. And I can add additional containers here, for example, add a new array element with the hyphen. Then let us, for example, say busybox as the new name of the new container, and the image is set to busybox as well. So now our code is clear, and as you can see, there are no errors. Now I don't really need the second container for now, so I'll just go ahead and delete this line and make sure that everything else is clean. Okay, so now let's save this file. Now let us check out another property of the editor. So if we click on the outline field here, we can see the entire data structure of the YAML file in a graphical format. So this is the YAML file on the right, and here you can see the 4 root elements here, the kind, and if I click on this, it'll highlight the line where we have the root element. So we have the API version, which is v1, we have kind, which is pod, and you'll see that it also has the other 2 root elements, for example metadata, which is a dictionary, as you can see with this curly braces here, which indicates a dictionary. And if you open that, you can see that the children of metadata, which the first one is labels, and labels is also a dictionary object, which has a value of env. So it presents in a hierarchical or a tree kind of structure, and similar to that we also have the spec section, which is a dictionary which has an array called containers, and you can spot an array using the double square brackets. And if I narrow it down, the first element of the containers array, which is the element 0, has 2 values, key value pairs, which has an image which is equal to nginx, and which has a name nginx as well. So this is quite handy to help you explore the structure of the file if you are not sure what's wrong and where. So we have successfully created our pod definition file easily using the YAML extension and the auto completion features. So we can now create a pod from this YAML file from the command line as you normally would. So you would go to the terminal and just type the ls command, and you can see that the nginx YAML file is here under the Kubernetes for beginners directory. And just let us quickly view this file. And you can see that it's exactly as it's supposed to be. And you could now create a pod using the kubectl create or apply command and passing in this file as input. Okay, so in this in the upcoming coding exercises section, you will first gain practice on getting the YAML files right. Okay, so if you are already familiar with YAML files and the formatting, etc., then feel free to skip those. But if you are new, we've created these coding exercises so that you get really comfortable with YAML files, especially the Kubernetes YAML files, before you actually head into the real labs. So just like the coding exercises that you worked with earlier, feel free to work through these, and then once you're done with these coding exercises, then you'll have the real lab environments where you will explore existing pods and creating new pods on real Kubernetes clusters by developing YAML files. Okay, so that's it for this lecture, and I will see you in the next one. Hello, in this video I will explain how to access labs part of this course. This course comes with real hands-on labs that you can access right in your browser. Students who purchase this course can get access to the labs for free on CodeCloud. You don't have to make any extra payments. To access the labs, there is a lecture named Access Labs in your course, right before the first lab starts. In the lecture, there is a link with a coupon code to enroll in the labs. Use the link to go to the checkout page on CodeCloud and apply the coupon code to gain access to the labs for free. If you haven't signed up on the CodeCloud website before, you will need to provide your email address. A temporary password will be emailed to you so that you can log in. So you must create an account and sign up on CodeCloud to access the labs. Once logged in, you can find your course under the courses page. Lab courses start with the term labs in their name. Once the labs are open, use the maximize button to hide the course curriculum to get more space for your labs. And if you want to see the course curriculum again, click on the same button. And to turn on dark mode, click the theme toggle button in the top right corner of your screen. Once you're done working on a lab, mark it complete using the Mark Complete button. As you can see, there are multiple lab scenarios for each course. I wish you all the best, and if you run into issues with accessing labs, please write to support@codecloud.com. I hope you have a great learning experience from us. Okay, so let's go over
the solution for the labs on pods. So in this lab, we're going to get familiar with pods. So the first question is, how many pods exist on the system? Now, we know that we can get the information about pods using the kubectl get pods command. That's what we learned. So we're going to run the kubectl get pods command. And you can ignore this line here that says in the current default namespace. So we're going to talk about namespaces in one of the upcoming lectures. So you don't have to worry about that for now. This is for those who already know what a namespace is. If you know, then just make sure you're checking the number of pods in the current default namespace. Okay, so when we run the kubectl get pods command, we see the result is 0. There are no resources found. So we're going to select 0 here. Okay, so the next is a task. So we've got to create a new pod with the Nginx image. So to create a pod, the easiest way is to run the kubectl run command, and we specify the image. So we have to specify a name and an image. So if you're not sure about the syntax, run the help command, and we see it's the name of the pod followed by the image, this format. So we're going to run that. Kubectl run. And since there's no specification about the name of the pod, so we could basically name it anything, but the image name has to be Nginx. Okay, so the pod is created. Okay, now how many pods are created now? We've created a few more pods, so please check again. So let's run the get pods command. Okay, so in addition to the Nginx pod that we created, there are a few other pods that were created by us, basically. So there are in a total 1, 2, 3, 4 pods at the moment. So let's select 4. What is the image used to create the new pods? You must look at one of the new pods in detail to figure this out. So let's pick one of the pods, this one. And we know that to look at it in detail, we've got to run the kubectl describe command. Okay, so now we have additional details about the pod. So this is the name of the pod, and you have the start time and a number of other details. So the question is, what is the image used to create the new pods? So we know that this tells us the containers, and here you have the image, and the image is busybox. So let's select busybox. Okay. Now, which nodes are these pods placed on? You must look at all the pods in detail to figure this out. So one way to do this is we've already run the kubectl describe pod command, and we can see that this is on node control plane, and we could actually run the describe command against each pod. So that's one way to figure that out. Another way, and an easier way, is to just run kubectl get pods command with the wide option. And here you get to see the node, and it says control plane. So all of the new pods are created on the control plane node. Select control plane. Okay, and how many containers are part of the pod web app? So there's a new pod created. Let's run get pods command to see web app. Okay, so if you look at this column right here, it shows us the total number of containers part of the pod. So this number right here is the total number of containers. So that's one way to figure that out, or you could always run the describe command to see that in detail. So here you see containers, and then you have one container here, it's Nginx, and the other one right here. So those are the two containers. So select 2. Then you have what images are used in the new web app pod. You must look at all the pods in detail to figure this out. Actually, it should be you must look at all the containers in detail. So here you have 2 containers. And if you look here, you see that the image for Nginx is Nginx, and the one for agent X is called agent X. So there's Nginx and agent X. Those are the images used for those containers. So this one. Okay, now what is the state of the container agent X in the pod web app? So if you look at the container here, and you see there is a state, and it is in a waiting state at the moment. So out of these, it's not running, ready, or success. It's actually error or waiting. So this is the state. Okay, now why do you think the container agent X in pod web app is in an error or waiting state? So try to figure it out from the events section of the pod. So if you look at one of the section here under state, you have the reason called as error image pull. Or if you just look at it below here in the event section, you can see the error, which is basically this one. It says fail to pull image agent X and at docker.io/library/agentx. So this image by the name agentx does not exist. And that's basically the reason that is failing. So the correct answer is a Docker image with this name doesn't exist on Docker Hub. Okay, now what does the ready column in the output of the kubectl get pods command indicate? So if you go up here, we have the output of the get pods command. And here you see you have 1/1 here, and then you have 1/2. So what does this mean? Now we know that this is the total containers within the pod. And this is basically, of course, the ones that are ready. So at the moment, there's only one ready out of the two. And we know that because this image does not exist. And of course, that's why that container isn't ready yet. So it's basically the total containers that are ready slash just the total containers within the pod. So that's total containers in the pod, or running containers in the pod slash total containers in the pod. So that's the correct answer. Okay, so the next task is to delete the web app. So let's run the kubectl delete command and delete the web app pod. Okay, that's deleted. Let's go to the next one. I create a new pod with the name Redis and with the image Redis123. And the recommendation is to use a pod definition YAML file, and the image name is wrong. Yeah, so the image name is wrong. So we could do this in 2 ways. So as we know, we could run the kubectl run command, and the name of the pod is Redis, and the name of the image is Redis123. You could basically just create it like this, but we just want to get familiar with generating the YAML file and creating it with the pod definition file. So let's use the dry run option and output the commands in a YAML format. Okay, so this is basically command, and it says the dry run command is deprecated. It is replaced with the dry run equals client. So let's run that. Okay, so this is the YAML file. So let's direct it to a file. We'll call it redis.yaml. So we have the YAML definition for that pod in this file. So we're now going to create the pod using the kubectl create or apply command. So let's go with the create command. Okay, so it's created. Let's verify that it's created. Okay, so it's created and it's in an error image pull state because we have the wrong image name. So that's fine. Let's click on check. Okay, successful. And the last question for this lab is to change the image on this pod to Redis to fix that error that we purposefully created, and to get the pod in a running state. So again, there are two ways to do that. You could run the kubectl edit command to edit the pod, or since we already have the Redis file, we could just go in and change the file and update it. So let's go and do that. Okay, I've changed the image name. I'm just going to apply the changes. Okay, let's check status. Now we'll talk about this error message later when we talk about imperative commands and the declarative way that we apply. But for now, let's stick to the basics and let's just make sure the change was successful. All right, so when I run the kubectl get pods command, we see that the pod is in a running state. Let's run check. All right. Okay, so that's the end of the lab. Let's hit the end lab button, and I'll see you in the next one.
Hello and welcome to this lecture on Kubernetes controllers. Controllers are the brain behind Kubernetes. They are the processes that monitor Kubernetes objects and respond accordingly. In this lecture, we will discuss about one controller in particular, and that is the replication controller. So, what is a replica and why do we need a replication controller? Let's go back to our first scenario where we had a single pod running our application. What if for some reason our application crashes and the pod fails? Users will no longer be able to access our application. To prevent users from losing access to our application, we would like to have more than one instance or pod running at the same time. That way, if one fails, we still have our application running on the other one. The replication controller helps us run multiple instances of a single pod in the Kubernetes cluster, thus providing high availability. So does that mean you can't use a replication controller if you plan to have a single pod? No. Even if you have a single pod, the replication controller can help by automatically bringing up a new pod when the existing one fails. Thus, the replication controller ensures that the specified number of pods are running at all times, even if it's just 1 or 100. Another reason we need replication controller is to create multiple pods to share the load across them. For example, in this simple scenario, we have a single pod serving a set of users. When the number of users increase, we deploy additional pod to balance the load across the two pods. If the demand further increases and if we were to run out of resources on the first node, we could deploy additional pods across the other nodes in the cluster. As you can see, the replication controller spans across multiple nodes in the cluster. It helps us balance the load across multiple pods on different nodes as well as scale our application when the demand increases. It's important to note that there are two similar terms, replication controller and replica set. Both have the same purpose, but they're not the same. Replication controller is the older technology that is being replaced by replica set. Replica set is the new recommended way to set up replication. However, whatever we discussed in the previous few slides remain applicable to both these technologies. There are minor differences in the way each works, and we will look at that in a bit. As such, we will try to stick to replica sets in all of our demos and implementations going forward. Let us now look at how we create a replication controller. As with the previous lecture, we start by creating a replication controller definition file. We will name it rc-definition.yaml. As with any Kubernetes definition file, we have 4 sections: the API version, kind, metadata, and spec. The API version is specific to what we are creating. In this case, replication controller is supported in Kubernetes API version v1. So we will set it as v1. The kind, as we know, is replication controller. Under metadata, we will add a name and we will call it myapp-rc, and we will also add a few labels, app and type, and assign values to them. So far, it has been very similar to how we created a pod in the previous section. The next is the most crucial part of the definition file, and that is the specification written as spec. For any Kubernetes definition file, the spec section defines what's inside the object we are creating. In this case, we note that the replication controller creates multiple instances of a pod. But what pod? We create a template section under spec to provide a pod template to be used by the replication controller to create replicas. Now, how do we define the pod template? It's not that hard because we have already done that in the previous exercise. Remember, we created a pod definition file in the previous exercise. We could reuse the contents of the file to populate the template section. Move all the contents of the pod definition file into the template section of the replication controller, except for the first few lines, which are API version and kind. Remember, whatever we move must be under the template section, meaning they should be intended to the right and have more spaces before them than the template line itself. They should be children of the template section. Looking at our file now, we now have 2 metadata sections. One is for the replication controller and another for the pod, and we have 2 spec sections, one for each. We have nested 2 definition files together, the replication controller being the parent and the pod definition being the child. Now there is something still missing. We haven't mentioned how many replicas we need in the replication controller. For that, add another property to the spec called replicas and input the number of replicas you need under it. Remember that the template and replicas are direct children of spec sections, so they are siblings and must be on the same vertical line, which means having equal number of spaces before them. Once the file is ready, run the kubectl create command and input the file using the -f parameter. The replication controller is created. When the replication controller is created, it first creates the pods using the pod definition template, as many as required, which is 3 in this case. To view the list of created replication controllers, run the kubectl get replication controller command and you will see the replication controller listed. We can also see the desired number of replicas or pods, the current number of replicas, and how many of them are ready in the output. If you would like to see the pods that were created by the replication controller, run the kubectl get pods command and you will see 3 pods running. Note that all of them are starting with the name of the replication controller, which is myapp-rc, indicating that they are all created automatically by the replication controller. What we just saw was the replication controller. Let us now look at replica set. It is very similar to replication controller. As usual, first we have API version, kind, metadata, and spec. The API version, though, is a bit different. It is apps/v1, which is different from what we had before for replication controller, which was just v1. If you get this wrong, you are likely to get an error that looks like this. It would say no match for kind replica set, because the specified Kubernetes API version has no support for replica set. The kind would be replica set, and we add name and labels in the metadata. The specification section looks very similar to replication controller. It has a template section where we provide pod definition as before. So I'm going to copy contents over from pod definition file, and we have number of replicas which is set to 3. However, there is one major difference between replication controller and replica set. Replica set requires a selector definition. The selector section helps the replica set identify what pods fall under it. But why would you have to specify what pods fall under it if you have provided the contents of the pod definition file itself in the template? It's because replica set can also manage pods that were not created as part of the replica set creation. Say, for example, there were pods created before the creation of the replica set that match labels specified in the selector. The replica set will also take those pods into consideration when creating the replicas. I will elaborate this in the next slide. But before we get into that, I would like to mention that the selector is one of the major differences between replication controller and replica set. The selector is not a required field in case of a replication controller, but it is still available. When you skip it, as we did in the previous slide, it assumes it to be the same as the labels provided in the pod definition file. In case of replica set, a user input is required for this property, and it has to be written in the form of match labels as shown here. The match labels selector simply matches the labels specified under it to the labels on the pod. The replica set selector also provides many other options for matching labels that were not available in a replication controller. And as always, to create a replica set, run the kubectl create command providing the definition file as input. And to see the created replicas, run the kubectl get replica set command. To get list of pods, simply run the kubectl get pods command. So what is the deal with labels and selectors? Why do we label our pods and objects in Kubernetes? Let us look at a simple scenario. Say we deployed 3 instances of our front-end web application as 3 pods. We would like to create a replication controller or replica set to ensure that we have 3 active pods at any time. And yes, that is one of the use cases of replica sets. You can use it to monitor existing pods if you have them already created, as it is in this example. In case they were not created, the replica set will create them for you. The role of the replica set is to monitor the pods, and if any of them were to fail, deploy new ones. The replica set is in fact a process that monitors the pods. Now, how does the replica set know what pods to monitor? There could be hundreds of other pods in the cluster running different applications. This is where labeling our pods during creation comes in handy. We could now provide these labels as a filter for replica set. Under the selector section, we use the match labels filter and provide the same label that we used while creating the pods. This way, the replica set knows which pods to monitor. The same concept of labels and selectors is used in many other places throughout Kubernetes. Now, let me ask you a question along the same lines. In the replica set specification section, we learned that there are 3 sections: template, replicas, and the selector. We need 3 replicas, and we have updated our selector based on our discussion in the previous slide. Say, for instance, we have the same scenario as in the previous slide, where we have 3 existing pods that were created already, and we need to create a replica set to monitor the pods to ensure there are a minimum of 3 running at all times. When the replication controller is created, it is not going to deploy a new instance of pod, as 3 of them with matching labels are already created. In that case, do we really need to provide a template section in the replica set specification, since we are not expecting the replica set to create a new pod on deployment? Yes, we do. because in case one of the pods were to fail in the future, the replica set needs to create a new one to maintain the desired number of pods. And for the replica set to create a new pod, the template definition section is required. Let's now look at how we scale the replica set. Say we started with 3 replicas, and in the future we decided to scale to 6. How do we update our replica set to scale to 6 replicas? Well, there are multiple ways to do it. The first is to update the number of replicas in the definition file to 6. Then run the kubectl replace command to specify the same file using the -f parameter, and that will update the replica set to have 6 replicas. The second way to do it is to run the kubectl scale command, use the replicas parameter to provide the new number of replicas and specify the same file as input. You may either input the definition file or provide the replica set name in the type name format. However, remember that using the file name as input will not result in the number of replicas being updated automatically in the file. In other words, the number of replicas in the replica set definition file will still be 3, even though you scaled your replica set to have 6 replicas using the kubectl scale command and the file as input. There are also options available for automatically scaling the replica set based on load, but that is an advanced topic and we will discuss it at a later time. Let us now review the commands real quick. The kubectl create command, as we know, is used to create a replica set, or basically any object in Kubernetes depending on the file we are providing as input. You must provide the input file using the -f parameter. Use the kubectl get command to see list of replica sets created. Use the kubectl delete replica set command followed by the name of the replica set to delete the replica set. And then we have the kubectl replace command to replace or update the replica set, and also the kubectl scale command to scale replica set simply from the command line without having to modify the file. That's it for this lecture.
In this demo, we're going to create replica sets based on the pod definition file that we created earlier. So in the last demo, we created pods using YAML. So here what I've done is I've created a directory called pods under the Kubernetes for Beginners directory, which is my project directory. And here are the 2 files that we created earlier for pods. So now let us create a new directory for replica sets called replica sets. And inside this directory, let's create a new file called replicaset.yaml. So let's start with the API version. And if you remember from the lecture, the version for replica set should be apps/v1. And next we'll use kind, and we'll use the suggestions available. And here we are going to make use of replica sets. The next root element is the same as that of the pod. So we are going to add metadata. And the name of the replica set, which should be my app-replica set. And we'll assign a label for our replica set as well. So the key would be app and the value will be my app. Now I'm going to set the last property, which is spec. And as you can see for replica set, the Visual Studio Code extension, the YAML extension, is automatically understood that the object is replica set and that it needs a selector. So it has already created the selector field for us. So we'll just have to fill it in. So here we are, and we have 2 possible options. It can be match expressions or match label. So let's use the match label option. And here we're going to use the same label that we used for the pod. We'll tie the pods to the replica set. So let us use the same label that we used before while creating pods. So for this, let me first open the Nginx pod definition file on the right side of the screen. So you can just right click and open it on the right side. The labels we used there were the env label, which is set to production. So I'm just going to copy that over. Now the next property is replicas. So for this example, let's make use of 3 replicas. And then the next mandatory value that we need to add here is the template. So For template, we can make use of the pod definition file that we created earlier and copy the template. So I'm just going to copy this whole section here from metadata and paste it under the template section. So now, as soon as we paste the contents, we see that the indentation is all out of order. So in order to fix this, one easy way to do it is to select the whole section that we just pasted, except for the first line, and then press tab twice, and then or until it fixes the indentation, right? Now, some editors are intelligent enough to automatically correct that for you, right? However, this one doesn't. But I know that there's an extension available for this. So if you're interested in that, check it out. I think it's called paste and indent or something like that. Okay, so for now, we will just stick to the manual way of fixing it. So now the format is corrected and there are no more errors in the file. So one thing to note here is the labels used for the pod and the labels used under the selector at the top. So they have to be the same, right? The label used at the top of the replica set itself doesn't really matter. It is the two labels that are set on the pod and then the one set on the selector that matters. That's what ties them together. So they have to be the same. So say we change the labels on the pod template to something else like app and set it to my app, then we must change it at the top as well to use the same, right? So now we're done with the file. Okay, so now that we have the replica set definition file ready, let's go back to the terminal, and here in the project root directory, we see that we have the new directory called replica sets. And underneath that, there is the replica set YAML definition file that we just created. So let's quickly check to make sure that the file has the contents we created. So I'm just going to use cat to view the contents of the file. So it has everything as expected. So now let me clear the screen, and we're going to create this replica set using the kubectl create command with the -f option. So as soon as the replica set is created, let's check the status using kubectl get replica set command. And we notice that there is one replica set which is created already. The desired number of replicas is equal to 3, and the current and ready number of replicas are 3 as well. And it was created about 8 seconds ago. So we can further inspect the status of the pods by running the kubectl get pods command. And we notice here that we have 3 replicas or 3 pods for the replica set we created. And all of the pods have a unique name, but you will notice that the name of the pod begins with the name of the replica set, which is my app-replica set. So that way you can look at the pod, any pod, and you can identify that if it is a standalone pod or a pod that is part of a replica set. Now, all of them are in a running state. So we said that a replica set ensures that a sufficient number of replicas or pods are available at all times. Now let's see what happens if we were to delete one of these pods. So let's go back and copy one of the pod names. So in this case, I'm copying this one here that has a name that ends with 8nxxl. So I'm going to use the kubectl delete pod command, and I'm going to paste the pod name here. Whenever you delete a pod, it takes a few seconds for the pod to fully terminate. So just give it a few seconds for the pod to fully terminate. So once we get the prompt back, let's check the status of the pods again. But you'll notice that the replica set still has 3 pods running. And you'll notice that one of the pods was just created 15 seconds ago. And you'll notice that the name of the older pod that ended with the 8nxxl has been deleted, and a new pod with the name with a different name has been created. So that's the replica set ensuring that sufficient number of pods are always available on the cluster. Now, if you run the kubectl describe replica set command for the new replica set, we will see that the desired number of replicas is 3, and here we see more information about the replica set, just like what we saw with the kubectl describe pod command. So here we see the name of the replica set, the selectors, the label for the replica set itself. If you scroll down, you see the labels that the selector above makes use of, which is the labels on the pod. And we also see the Nginx container definition. And if you scroll down below, we see the events. So initially, when we created the replica set, it actually came up with 3 replicas, but then we deleted one of the replicas, and then it spun up one additional replica for it to maintain that desired number, right? And you see all of that in the history of events here. So this is a handy tool and command if you'd like to inspect what happened to a replica set in case you're troubleshooting something, or you're just looking for more information on what's happening with the replica set, etc. So we said that a replica set ensures that a minimum number of replicas are available all the time. But what if there are more number of replicas than what's required? So let's try something else. Let's try to create a new pod by making use of the same label that the replica set selector uses, which is the app set to my app. And to do this, let's go back to our pod definition file. And so here I have the nginx.yaml file that we created. And we'll notice that we have a pod template which tries to create a pod by the name nginx-2. But we also, but we have now changed its label to the same label as the pod definition template used in our replica set. So now let's create the pod directly, and not through the replica set, but just directly the pod, like as we have done before. And we'll see what happens when we create a new pod outside of the replica set, but one that has the same labels that the replica set selector uses. So before doing that, let me run the kubectl get pods command, and I see that there is only the 3 pods that were created by the replica set. And so now I'm going to use the kubectl create command with the -f option, and I'll specify the nginx.yaml file, and you will see that the nginx-2 pod has been created. But if I run the kubectl get pods command now, we'll see that the status of that pod is in a terminating state already. And the replica set is terminating the new pod that we just created. It's not allowing more pods with the same labels than the number of replicas configured on the replica set. So if we run the kubectl describe command now, we'll see that at the bottom, under the events section of the output of describe command, the replica set controller deletes the new nginx-2 pod that we just created. So now if I go back and run the kubectl get pods command, I see that it is under terminating state, and soon it should go away from the list altogether. Okay, so now let's see how to update a replica set. So what if we want to change the number of replicas to, say, 4 instead of the current 3? Say, for instance, we're trying to scale up our application. So for this, we must edit the replica set definition file and update its replicas count to 4. For this, we will make use of a new command called kubectl edit replica set, and we will provide the name of the replica set, which is my app-replica set. And now when we run this command, we see that it opens up the running configuration of the replica set in a text editor, in a text format. In this case, it opens up in Vim. So note that this is not the actual file that we used, that we created at the beginning of this demo. This is a temporary file that's created by Kubernetes in memory to allow us to edit the configuration of an existing object on Kubernetes. And that's why you'll see a lot of additional fields in this file other than the details that you provided. So changes made to this file are directly applied on the running configuration on the cluster as soon as the file is saved. So you must be very careful with the changes that you're making here. So now, if I scroll down all the way to the spec section, which is over here, and we can see the running configuration and the current number of replicas, which is set to 3, I can change this to scale it up by another pod, so 4 in this case. And then I will save and exit from the editor. Now it should now spin up a new pod in addition to the 3 that we already had to match the new number of replicas that we specified. So if we run the kubectl get pods command, now we see that there's a new pod which was spun up 6 seconds ago, and we can use the same approach to scale down as well. Now there's also a command available to scale the number of replicas without having to go in and edit the definition file, and that is using the kubectl scale replica set command. So we will provide the name of the replica set, and we will set the number of replicas for it to scale to 2. So you could specify a number which is greater or less than the current number of replicas. And take a note of the double dashes before the replicas option. So if I run the kubectl get pods command again, we will see that the replica set is now scaling down to 2 replicas by terminating 2 of the pods. Well, so let's wait for these 2 replicas to be terminated. And there you go. And now we just have 2 pods. Well, that's it for this demo. I will see you in the next.
Okay, so in this video, we're going to go over the solution for the lab on replica sets. So let's start with the first question. So the first question is, how many pods exist on the system? So just like before, we run the kubectl get pods command, and there are no pods at the moment, so select 0. The next question is how many replica sets exist on the system. So we run the kubectl get replica set command, and it's 0. Okay, so some changes were made, and let's check the replica set now, and we see that there is one created. So let's just select 1. Okay. Now the question is how many pods are desired in the new replica set? So we know that from the output, the desired number of pods in the replica set is number 4. So let's select 4. Now what is the image used to create the pods in the new replica set? So we can find that out by looking at the replica set in a bit more detail, and for that we know we have to run the kubectl describe command, and we're going to run describe replica set and then new replica set. You can hit the tab key to autocomplete the names of what you're looking for. Okay, so in this output we see the pod template and the image that's used. It's busybox 777. So that's the question, and here is the answer. So busybox 777. Now, how many pods are ready in the new replica set? So if you look at the output here, it says the number of pods that are ready are 0. You can also see the same kind of here, the pod status 0 running. So it is 0. Now, why do you think the pods are not ready? So if you look at this, you have, so we'll need to look at one of these pods in a bit more detail. Of course, it's obvious, but I just want to show you. If you're not sure what the error is, then you've got to look at one of these pods in a bit more detail. So let's run the kubectl describe command and look at any one of the pods in a bit more detail. And you see it's basically because it's failed to pull the image busybox 777, right? So the repository does not exist. So there's no image by the name busybox 777. That's a reason. So let's check that. Now the question is to delete any one of the pod. Sorry, it's clear. run the get pods command, and we've got to delete any one of these pods. Okay, so that's done. So how many pods exist now? Let's run the get pods command again. And we see that there's still 4 pods running, right? So even though we deleted one, the one that we deleted is not here, the one that starts with WK, but there are still 4 pods. So that exercise was just to show that even if you delete a pod, part of a replica set, it's automatically going to recreate a new one. And if you look at the age here, you can see that the new one that was created was just 17 seconds ago, as opposed to the other ones that have been running for 3 minutes or more. Okay, so why are there still 4 pods even after you deleted it? It's not because I didn't delete it properly. It's not because you cannot delete a pod from a replica set. It's because replica set ensures that the desired number of pods always run. Okay, so the next one is to create a replica set using the replica set definition file located at root. So let's look at where that is. So there's one here, and there's an issue with the file, so we have to try and fix it. So let's first try to create it. So kubectl create -f root replica set definitional.yaml. Okay, so the error is that it's unable to recognize this file, no matches for kind replica set in version v1. So there's something wrong here. Either the kind replica set is incorrect or the version v1 is incorrect. So let's look at the file. And we see that the API version is v1 and kind is replica set. And as we learned from the previous video, the API version is incorrect. But if you're not sure what it is, one way to find that out is using the kubectl explain command. So run the kubectl explain replica set command. Sorry. And here you can see the version. So the version is supposed to be apps/v1, right? So that's the problem. So let's go ahead and fix that. Apps/v1. And let's try and create that again. Okay, so this it has now been created. Okay, so let's go to the next one. So next task is to fix the issue in the second file and create the replica set. So let's try that. Let's just first try to create it. Okay, so it says there's an invalid value, selector does not match template label. So let's take a look at the file here. And we see the API version is apps/v1, which is correct. The kind is replica set. That also seems to be correct. The metadata is the name. And then you have the spec section. So you have replicas, you have selector. So there is something wrong here, which is why it didn't work. Let's find that out. So here it says invalid value, selector does not match the template labels. So basically the issue here is that you have the labels specified here called tier front end, and then the label for the pod that the replica set will create is Nginx. So these two should match. Otherwise, the replica set cannot basically manage the pods that it creates. So we've got to either change this to front end or change this to Nginx. But at the end, both of them should match. So let's change this to Nginx, save this file, and run it again. Okay, and that's now created. Okay, let's go to the next one. Now we've got to delete the two newly created replica sets. So let's first look at the status right now. You can also run just rs instead of replica set, which is the short form. And now we've got to delete both of these replica sets. So got to delete rs replica set 1 and 2. You can also give multiple in the same command. Okay, so that's done. Now fix the original replica set to use the correct BusyBox image. So we know that the first one, which is, we now only have one, and we know that there are none of the pods are in a ready state, and we also know that because the image name is incorrect, so we've got to now fix that. So for this, let's run the kubectl edit command and edit the new replica set. And let's go into the container section and change the image name to just BusyBox and save the file. And let's check status of pods now on the replica set. So it's still 0. Let's just give it some time for it to delete the old pods and create new ones with the new image. Provide rs. Okay, so when you update a replica set, even though the image name is updated, the pods are not automatically recreated, right? So you have to either delete and recreate the entire replica set, or you have to delete all the pods so that the replica set creates new pods with the new image name. So let's go back and let's look at pods, and you see they're all still in the error state. So we're just going to go through and delete them. We're gonna give the name of each one. And we'll just wait for all of them to be terminated. Let's run get pods again. Okay, it's in a creating state and it's in a running state. Let's check the status of the replica set now, and you can see that they're all in a ready state. Okay, let's go to the next one. Now we've got to scale the replica set to 5 pods. So let's run the kubectl scale command and specify the number of replicas to 5. Let's check the status, and we can see that a new pod has been added. We can also do that using the edit command. So we could do a kubectl edit rs and specify the name of the replica set, and then go here and just change this number to the desired number, and then save the file. But we're not going to do that right now. Okay, so that's done. And now the task is to scale the replica set down to 2 pods. So this time let's use the other approach. So let's edit the replica set. Go to the number here, set it to 2. Okay, let's check. Okay, so that's it for this lab. And next we'll look at deployments.
Hello and welcome to this lecture. In this lecture, we will discuss about Kubernetes deployments. For a minute, let us forget about pods and replica sets and other Kubernetes concepts and talk about how you might want to deploy your application in a production environment. Say, for example, you have a web server that needs to be deployed in a production environment. You need not one, but many such instances of the web server running for obvious reasons. Secondly, whenever newer versions of application builds become available on the Docker registry, you would like to upgrade your Docker instances seamlessly. However, when you upgrade your instances, you do not want to upgrade all of them at once as we just did. This may impact users accessing our application, so you might want to upgrade them one after the other. And that kind of upgrade is known as rolling updates. Suppose one of the upgrades you performed resulted in an unexpected error and you're asked to undo the recent change. You would like to be able to roll back the changes that were recently carried out. Finally, say for example, you would like to make multiple changes to your environment, such as upgrading the underlying web server versions, as well as scaling your environment and also modifying the resource allocations, etc. You do not want to apply each change immediately after the command is run. Instead, you would like to apply a pause to your environment, make the changes, and then resume so that all the changes are rolled out together. All of these capabilities are available with the Kubernetes deployments. So far in this course, we discussed about pods, which deploy single instances of our application, such as the web application in this case. Each container is encapsulated in pods. Multiple such pods are deployed using replication controllers or replica sets. And then comes deployment, which is a Kubernetes object that comes higher in the hierarchy. The deployment provides us with the capability to upgrade the underlying instances seamlessly using rolling updates, undo changes, and pause and resume changes as required. So how do we create a deployment? As with the previous components, we first create a deployment definition file. The contents of the deployment definition file are exactly similar to the replica set definition file, except for the kind, which is now going to be deployment. If we walk through the contents of the file, it has an API version, which is apps/v1, metadata, which has name and labels, and a spec that has template, replicas, and selector. The template has a pod definition inside it. Once the file is ready, run the kubectl create command and specify the deployment definition file. Then run the kubectl get deployments command to see the newly created deployment. The deployment automatically creates a replica set. So if you run the kubectl get replica set command, you will be able to see a new replica set in the name of the deployment. The replica sets ultimately create pods. So if you run the kubectl get pods command, you will be able to see the pods with the name of the deployment and the replica set. So far, there hasn't been much of a difference between replica set and deployments, except for the fact that deployment created a new Kubernetes object called deployments. We will see how to take advantage of the deployment using the use cases we discussed in the previous slide in the upcoming lectures. And one more note before we end this lecture: to see all the created objects at once, run the kubectl get all command. And in this case, we can see that the deployment was created, and then we have the replica set followed by 3 pods that were created as part of the deployment. That's it for this lecture. We will now head over to a demo, and I will see you in the next lecture.
In this demo, we're going to create a deployment. So let us create a new folder called deployments within our project directory. And within the deployments directory, I'm going to create a new file called deployment.yaml. And we're going to make use of the definition file that we created earlier for the replica sets, because it's quite similar to that of the deployment. And to make this easier, we're just going to open the replica set definition file on the right. So I'm going to use the split editor function here. So on the left, we have the deployment.yaml file that we're going to create now. And on the right, we have the replica set.yaml file that we created earlier. So as before, we will start off with the API version, and it is also going to be apps/v1, the same as replica set. And I'm going to use the kind as deployment. So let me select that from here. And then the metadata, I'm going to enter it here as well, and that will have the name and labels. And we're going to use the name as my app-deployment. And I will add a couple of labels as well. The labels will be a front end, tier front end, and maybe another one called Nginx. Okay, now the spec section is very similar to that of the replica sets. So I'm just going to copy this entire section here for the spec section, and I'm just going to paste it here. So that should be good enough for us to start the deployment. And I'm going to change I'm just going to reduce the number of replicas to 3. Okay, so let's go back to our terminal, and if we check the root of our project directory, we see the new directory that we created called deployments. And I'm going to create this deployment using the kubectl create command along with the -f deployment.yaml file. And as you can see, the deployment has been created. So let's run the kubectl get deployments command. And I can see that we have one deployment which is created, and it has 3 out of 3 ready pods, and available are 3 as well. So if you want to check the pod, we can run the kubectl get pods command, and I can see that we have 3 pods which are in a running state, which were created a few moments ago. Now let us run a kubectl describe deployment command. And the name of the deployment is my app-deployment. And here we can see a lot of similar information. So the name of the pod, the label of the deployment itself, and the front end label that we set. And we see the selector that we use the same as that of the replica set, which is equal to my app. And it has 3 desired and 3 available pods, and which are in a running state. And here's the pod section. The label of the pod is my app, and here's the container details with the image set to Nginx. If you scroll to the bottom, you'll see that it also has an event section, and it just shows the deployment controller a message which says that the replica set for this deployment has been scaled to 3. And now, before we move on, let's run the kubectl get all command, which shows all the objects which is created in the cluster. So you can see that we have one deployment, which is the deployment that we created, and there is a replica set which is created for that specific deployment called my app-replica set. And then we have the 3 pods which have been created using that replica set. Okay, well, that's it for now. Head over to the labs and try these out for yourselves.
Okay, so in this lab, we'll get introduced to deployments. So let us begin. The first question is how many pods exist on the system? So let's run kubectl get pods command. And we see there are no pods. And the next one is to identify the number of replica sets. and there are none. So the answer is 0. Okay, and now it's the number of deployments. So get deployments, and that's 0 as well. So it's a clean environment. There are no pods, no replica sets or deployments at the moment, but some changes have been made. So we'll now check the deployments again. Okay, so there is one deployment. Okay, so the answer is 1. Now, how many replica sets exist on the system? Now we know that there's one deployment. We do not know how many replica sets, so let's just run the get rs command again to check the number of replica sets. So that's one replica set. So basically the deployment called front-end deployment has now created a replica set named front-end deployment dash some numbers. So that's the name of the replica set that the deployment is created. And then let's also check the number of pods now. And there are 4 pods. So basically that's what we're trying to understand here. There was nothing before, but when we created a deployment, it's created a replica set, and then it's also created 4 pods. Now, out of all the existing pods, how many are ready? So if you look at the status here, out of 4 pods, 0 are ready. So let's select 0. And what is the image used to create the pods in the new deployment? So let's take a look at one of the pods in a bit more detail. Describe pod front-end deployment. And maybe we'll just pick one of the pod. And we see the image used is BusyBox 888. So let's select that. Now I know that there's a little bit of repetition between different exercises here, but this is mainly to get you familiar with some of these commands, right? The get commands and the describe commands. And I promise that we have more fun stuff coming up in the upcoming labs. So we're just getting started. Okay, so why do you think the deployment is not ready? And as before, we know that it's because the image BusyBox 888 does not exist. So let's select that. Okay, so the next task is to create a new deployment using the deployment definition 1 file in root. So we're already in root, so let's check this file. So let's try to create the deployment using the file. Okay, and it didn't go. It didn't go through, so there is some kind of error. So it says no kind deployment is registered for version apps/v1. So if we look at the file, we see that the API version is apps/v1, which seems to be correct, but the kind is deployment, which is also right, but the issue is that it's case sensitive, right? So the first character has to be a capital letter. So that's kind of the standard for kind. So the reason we have these kind of exercises is just to help you understand and learn how to, know what the issue is when you come up across these errors. So oftentimes you'll face these kind of errors because of these kind of typos or words not being spelled correctly or not in the right case, and you should know what those mean when you see these kind of errors. So there are possibilities that you may mix up the API version or kind, and we don't want to spend a lot of time during the exam just not knowing what those are. So that's the reason for these kind of exercises. So I've just fixed that, and let's proceed with the creation. Okay, so that went through. And the final task is to create a new deployment with the below attributes. So you have the name, you have the replicas, and you have the image. So to create an object, we know we can run the kubectl create command. And This time we want to create a deployment. And let's take a look at the help for that. And we see there are different options. So you can create a deployment, specify a name with an image. So we have a name and we have an image, but we also want to specify the number of replicas. So there is a command just for that. So you have the name, the image, and the replicas. So that's what we're going to follow. So run the kubectl create deployment command and specify the name, which is HTTPD frontend. And the image is, and it's good to create a practice of just copying and pasting from the question, as that will also help you in the exam if you are learning this for the purpose of giving the exam. And the replicas is number 3. Okay, so, and also make it a practice to always verify if what you did is right. So kubectl get deploy. We have the HTTPD frontend deployment, and we also want to make sure that it goes to a ready state. Yep. So 3 out of 3 are ready. Check our work. Okay, so that's done. And that's the end of this lab.
Hello and welcome to this lecture. In this lecture, we will talk about updates and rollbacks in a deployment. Before we look at how we upgrade our application, let's try to understand rollouts and versioning in a deployment. When you first create a deployment, it triggers a rollout. A new rollout creates a new deployment revision. Let's call it revision 1. In the future, when the application is upgraded, meaning when the container version is updated to a new one, a new rollout is triggered and a new deployment revision is created, named revision 2. This helps us keep track of the changes made to our deployment and enables us to roll back to a previous version of deployment if necessary. You can see the status of your rollout by running the command kubectl rollout status followed by the name of the deployment. To see the revisions and history of rollout, run the kubectl rollout history command followed by the deployment name, and this will show you the revisions and history of our deployment. There are 2 types of deployment strategies. Say for example, you have 5 replicas of your web application instance deployed. One way to upgrade these to a newer version is to destroy all of these and then create newer versions of application instances. Meaning, first destroy the 5 running instances and then deploy 5 new instances of the new application version. The problem with this, as you can imagine, is that during the period after the older versions are down and before any newer version is up, the application is down and inaccessible to users. This strategy is known as the recreate strategy, and thankfully this is not the default deployment strategy. The second strategy is where we do not destroy all of them at once. Instead, we take down the older version and bring up a newer version one by one. This way the application never goes down and the upgrade is seamless. Remember, if you do not specify a strategy while creating the deployment, it will assume it to be rolling update. In other words, rolling update is the default deployment strategy. So we talked about upgrades. How exactly do you update your deployment? When I say update, it could be different things, such as updating your application version by updating the version of Docker containers used, updating their labels, or updating the number of replicas, etc. Since we already have a deployment definition file, it is easy for us to modify this file. Once we make the necessary changes, we run the kubectl apply command to apply the changes. A new rollout is triggered and a new revision of the deployment is created. But there is another way to do the same thing. You could use the kubectl set image command to update the image of your application. But remember, doing it this way will result in the deployment definition file having a different configuration. So you must be careful when using the same definition file to make changes in the future. The difference between the recreate and rolling update strategies can also be seen when you view the deployments in detail. Run the kubectl describe deployment command to see the detailed information regarding the deployments. You will notice when the recreate strategy was used, the events indicate that the old replica set was scaled down to 0 first, and then the new replica set scaled up to 5. However, when the rolling update strategy was used, the old replica set was scaled down one at a time, simultaneously scaling up the new replica set one at a time. Let's look at how a deployment performs an upgrade under the hood. When a new deployment is created, say to deploy 5 replicas, it first creates a replica set automatically, which in turn creates the number of pods required to meet the number of replicas. When you upgrade your application, as we saw in the previous slide, the Kubernetes deployment object creates a new replica set under the hood and starts deploying the containers there, at the same time taking down the pods in the old replica set following a rolling update strategy. This can be seen when you try to list the replica sets using the kubectl get replica sets command. Here we see the old replica set with 0 pods and the new replica set with 5 pods. Say for instance, once you upgrade your application, you realize something isn't very right. Something's wrong with the new version of build you used to upgrade. So you would like to roll back your update. Kubernetes deployments allow you to roll back to a previous revision. To undo a change, run the kubectl rollout undo command followed by the name of the deployment. The deployment will then destroy the pods in the new replica set and bring the older ones up in the old replica set, and your application is back to its older format. When you compare the output of the kubectl get replica sets command before and after the rollback, you will be able to notice this difference. Before the rollback, the first replica set had 0 pods and new replica set had 5 pods, and this is reversed after the rollback is finished. To summarize the commands real quick, use the kubectl create command to create the deployment, get deployments command to list the deployments, apply and set image commands to update the deployments, and rollout status command to see the status of rollouts, and rollout undo command to roll back a deployment operation.
In this demo, we're going to look at updates and rollbacks for deployments in Kubernetes. So in the previous demo, we used a deployment definition file, which is located in the deployment directory of our project folder. The name of the deployment is my app deployment, and we have updated the file to use 6 replicas. Earlier, it was 3, and it is using an Nginx image. So to create this deployment, we will use the kubectl create deployment command. But before that, let's quickly check and make sure that there are no objects created in the cluster. Okay, so that looks good. So I'm going to run the kubectl create command with the -f option to specify the deployment.yaml as the file. So once we run this command, the deployment is created. Now let's make use of a new command called the kubectl rollout status command with the deployment name to check the status of the deployment. So as soon as I run this command, I see that the deployment my app-deployment has been successfully rolled out. Now, if we had run this command more quickly, like right after we ran the command to create the deployment, we would have seen a different status. So let's quickly delete this deployment. And what I'm going to do now is I'm going to create the deployment again, and I'm going to quickly run the status command right after I do it. As soon as I run this command, it will show you the status of each replica which is being brought up. So remember that we have used 6 replicas in total, and as soon as we run the status command after deleting the deployment, we see that it tries to bring up the pod one at a time. So here we have 0 out of 6, and then 1 out of 6, 2 out of 6, etc. So until all the 6 pods are up and running, you'll see a status message related to that. And only after all the pods have been deployed successfully will Kubernetes consider the deployment to be successful. So once deployed, we use another command to see the history of the deployment. And for this, we will use the same command as before, but instead of status, we will use the rollout history command. Now you can see that the My App deployment has one revision, which is the one that we just did, that was creating the deployment itself. And there's also a column called change cost, which you'll notice that there is no change cost specified. And that is because we did not specifically ask it to record the cause of change while we created the deployment. So let's go back and fix that. So we'll delete the deployment again. Let's wait for the pods to be terminated. So now it's in a terminating state, and let's wait for all of them to go away. So now that all of them have been deleted, I'm going to run the same command as before, but this time I'm going to use the --record option. The record option instructs Kubernetes to record the cause of change. So we will execute that command now. And again, I'll run the rollout status command to watch the status of deployment and wait for all the pods to be up and for the deployment to be successful. And now let's run the history command again, and this time you'll see that against the revision there is a change cause which is mentioned, which is essentially the same command that we ran to create the deployment. But because we use the --record option, it is recording the command here. So now let us try to make a change to the deployment. So first let's run the kubectl describe command with the name of the deployment. And this pulls up the additional information, and you'll see that in the annotations section it has recorded the command that we used to run this to create this deployment. And we know that it is running 6 replicas, and if you scroll down you'll see that the image of this container of this deployment is Nginx. So let's make a change to that, and for this I'll make use of the kubectl edit deployment command. And I'm also going to use the --record option so that the cause of change is tracked in the revision history. So what I'm going to do now is I'm going to look up image, and currently it is set to Nginx. So we will change this to a lower version. So this is using the latest version of Nginx currently, and what we'll do is we will change it to another version, a lower version, and for that let's make use of the Docker Hub documentation. So here I'm at Docker Hub, and I'm looking at Nginx, and you'll see that the current version, since we did not specify a target, is 1.19 as of this recording. And let us make use of an older version, 1.18. So back to the terminal, I'm going to change the version to 1.18. And for that, I'll add a colon, and I'll mention the version number here. And once I'm done with the changes, I'll use the WQ to save and exit the editor. And now, if you're on the status command, you will see a familiar screen where it is bringing up the new pods. But you'll also notice that in the screen, we see that the old pods are getting terminated. So one after the other, the new pods are being created with the new image, whereas old pods are getting terminated. So since the default update strategy is set to rolling update, Kubernetes deployments are intelligent enough to make sure that there are some running pods in the system so that the end users are not affected, and it does the update one after the other. So now let's run a kubectl describe command against the deployment, and you'll see the same thing under the event section as well. So you can see that the older replica sets have been scaled down along with the replica set IDs, which were running the older image, and the new ones are scaled up. And here we can see the revision and the cause of change, which is kubectl edit deployment, which we ran to change the image. And here we take a look at the image quickly, and we can see that it is running Nginx 1.18. Right, so now let's make yet another change to our deployment. So right now it's running Nginx version 1.18. Say we have a requirement to use a different image instead of this. So one way to do that is to use the kubectl edit deployment command and edit the image name within the YAML file that opens. Another way to do is to use another command called kubectl set image deployment, and the name of the deployment, which is my app deployment. And here I'm going to use the name of the container, which is Nginx. And this is a key value format way of specifying the value. So this should have the value of the new version that we're going to set. So let's make use of the Docker Hub page, and the new version that we will use is, say, 1.18-Perl. Again, I'm going to make use of the record command, the record option, while I do this, so the changes are recorded in the rollout history. So now let's run a quick status command, and we can see that the older replicas are getting terminated, which is for version 1.18, and we should have new replicas up and running for the version 1.18-Perl. So a quick look at the history shows us that it's all set, and we have the new version, which is version number 3, where we update the image using the kubectl set image command. So let's quickly run the kubectl get pods command and make sure that all the 6 pods are running. So let's say there is an issue with this new image that we used, and it's not working well for the end users. We can revert back to the previous version by using the kubectl undo command. So right now we are on a revision 3, and we want to move to revision 2, which has the Nginx 1.18 version. And to do this, we can run the kubectl rollout undo command with the name of the deployment. So again, let's run kubectl status command, and we see that it is making the change, and it is bringing down the older replicas of revision number 3, and then reverting back to revision number 2, which runs the Nginx 1.18 image. Let's run a kubectl describe deployment command to make sure that this command in fact switched to the correct image. So it has reverted back to Nginx 1.18 image. So now let's take a quick look at the rollout history and see what is recorded there. Now you'll see that we still have 3 revisions in total. There is a new revision which is now created, which is number 4, but the revision number 2 is gone. Now that's because the 4th revision, which is the new revision, is essentially just the same as the 2nd revision. So it's reverted back to the same state that deployment was on when it was at revision 2. So essentially revision 2 has become the latest revision, but it has changed the revision number from 2 to 4. And this is the same command that was recorded for revision 2 as well. Now let's try out another scenario. So I'm going to use the kubectl edit command again and make some more changes to our deployment. Now we know that right now the image should be on 1.18 because we reverted in the last step. So now I'm going to make a change for the Nginx container to use an image that does not exist. So let me put something random here, such as does not exist, and I'm going to save this file, and we'll see the status now. So now you can see that the rollout status is stuck with this message that says waiting for a rollout to finish, and that 3 out of 5 new replicas have been updated. It's going to stay there as it's trying to update to an image that does not exist, and it's not able to pull that image from Docker Hub, so the containers would fail. So as a result, it will not successfully complete those deployment. Now let's go back and check. We'll run the kubectl get deployment command, and we provide the name of the deployment. And here we see that the ready state for this deployment is now 5 out of 6. Now up to date is 3 and available is 5. And let's also quickly run kubectl get pods command. And here you'll notice that the number of pods which are running is actually 5. So here the deployment has terminated one of the existing pods on version 1.18, and it has tried to create 3 new pods with the new version of the image, the one that does not exist, and that's why they are all in an error state. So the status of the new pods are image pull back off, so all of these 3 have failed because the image by that name that we specified does not exist on Docker Hub. And as a result, it will keep the deployment in its current state until it is able to fetch this new image from Docker Hub. So even though we have specified a wrong image and there are 3 new pods which are trying to load the new image, the application is not impacted and the end users will still be able to access the application on the old 5 running pods. And this is because since we set the strategy to rolling upgrade, Kubernetes will only downgrade or destroy the older pods once we have sufficient newer pods available. So now let's take a look at the revision history, and you will see that a new revision, which is revision number 5, is recorded as well. So now as a final step, let us do an undo deployment operation so that it goes from revision number 5 back to revision number 4 and fix the name of the image back to Nginx 1.18. So for that, I'm going to use the rollout undo command again. And let's run the rollout status real quickly. And now you'll see that it is successful. So let's check the status of the pods, and we see that the one that it had to recreate has been created 12 seconds ago. And the remaining 5 pods were already in the correct version of 1.18. And it terminated the 3 new pods, which was trying to make use of the wrong image. So now let us run a describe command, and we will see that our application is now on the correct version, which is Nginx 1.18, and everything's good. Well, that's it for now, and I will see you in the next lecture.
Okay, so in this lab, we're going to look at rolling updates and rollbacks. So rolling updates mainly. So going forward, I'm going to try and use the alias K for kubectl. So I've already set an alias K for kubectl. So I'm going to try and use that going forward. So we have deployed a simple web application, inspect the pods and services. So let's do get pod. So there seems to be a front end, a set of front end pods. Most likely there is a deployment. Look at, so there's a front end deployment which deploys 4 pods. Then wait for the application to fully deploy and view the application using the link called Web App Portal. So there is a link here you can click to view the application, and it opens it up in a new window. It's called, it just says hello front end. Moment. Okay, so let's look at the first or second question. So what is the current color of the web application? So if you look here, it is blue in color. So it's blue. Now run the script named call test to send multiple requests to the web application. So we have call test here, so I'm going to run that. As you can see, all it does is it pings the application and returns the color. So the color is blue. And it just keeps running that for a few seconds. So that's done. So we're going to use this script to run tests to kind of simulate accessing the web application by either like multiple users, so or sending multiple requests to the web application. So we'll use that to basically just do a small round of tests on the application. Now inspect the deployment and identify the number of pods deployed by it. So we just looked at that and we saw that it creates 4 pods. So it's 4. That's the answer here. Now, what container image is used to deploy the application? So let's look at the deployment in more detail. And content. And here we have the pod template. We have containers, image. The image is CodeCloud/web app color v1. So it's this one right here. That's the image we've used to deploy the application. Now inspect the deployment and identify the current strategy. So if you look at this, we have the strategy type given here, and that is rolling update. So that's the rolling update is the current strategy. Now, if you were to deploy, if you were to upgrade the application now, what would happen? So we know that the rolling update takes down one pod at a time and brings up the new pod. So it does not wait. It does not take all of it down and bring the new ones up. So answer here is all pods are taken down before upgrading. No, that's not the correct one. Pods are upgraded a few at a time. So that's the correct one. Now let us try that. Upgrade the application by setting the image on the deployment to CodeCloud Web App Color v2. So we're going to update the image. Now one way to do that is you could do a kubectl edit and deployment and front end, and then go here and change the image. Another way to do that is just using the kubectl set command. So you could do a set image. Let's run the help to find that out. So that's kubectl set image. You can say deployment name, and then the container name and the image, right? So let's try that. So that's kubectl set image for the deployment. The deployment name is front end, and the container name, we need to find out the container name. So let's do a deploy front end. The container name is simple web app. Okay, so let's do that again. Kubectl set image deploy front end. Container name is simple web app equals, that's the image, and that's updated. Let's make sure it's updated. Let's run the describe command again, and we see that the image is set to v2. Okay, that's success. So let's run the curl test again and see what we're seeing. So we're still seeing blue, but we see green occasionally. So there's a lot of blue and there's some green. So green is the new version that we have deployed, and blue is the older version. And now we have a lot of green, right? So if you look at this, there was a lot of blue at first, and then there's some green, and then there's green and blue at one point of time, and then we just have green. So that's how it's updated the application deployment. So that's the rolling update. Now, up to how many pods can be down for upgrade at a time? Consider the current strategy settings. So if you look at this, the strategy type is rolling update, which we have already seen. There's rolling update strategy, the additional details here. So 25% max unavailable. So that means it's going to take down only 25% of the pods at a time before bringing the new ones up. So you have 4 replicas, and 25% of that is just 1. So let's select 1. Now change the deployment strategy to recreate. and delete and recreate the deployment if necessary. So let's go ahead and try and change the deployment strategy. So let's do a kubectl edit, deployment, front-end, and we'll just go here and we'll just change this strategy type to recreate. And the recreate does not require the rolling update parameter, so we're just going to get rid of this. Okay, and let's verify. And we see the strategy tab is changed to recreate. Okay. Now the next one is to upgrade the application by setting the image on the deployment to v3. So currently we have v2 and we've got to change it to v3. And let's use the same command, the kubectl set image deploy command, and we'll now just change this to 3. Okay, so that's updated. And next, let's run the curl test again. And when we run this time, unlike the previous time, we see a lot of failures. So some of the requests are failing, and this is because it took down some of the pods as part of the upgrade because we are doing a recreate. So let's just give it some time. If you look at the application here, it says bad gateway. Okay, and now we can see it started to respond. We have the red colors coming up, and when we refresh this, you see that we have application v3 and the red colors are coming up. Okay, so that's the end of this lab.